Hi students. So let's work out a brief definition of flux. So the flux is the quantity that actually has physical meaning. We may be talking about magnitudes, but the linear quantity is the flux. So the energy flux is an intuitive measurement of energy flow. Imagine that you have a detector of area A, this detector here, and you collect radiation with it for a time interval t. Now, if the source is constant, the amount of energy that you collect will be proportional to both the area and to the time. To be able to write the proportionality, we consider that even if the energy source is varying, during an infinitesimal time interval dt, the source can be considered to be constant in time. So likewise, if the area is too large, you may have the different areas of the detector can also be detecting different amounts of energy. So we're also going to consider the area to be infinitesimal. Then in this infinitesimal patch, dA, the energy is going to be spatially uniform. And because we're also defining the time interval to be infinitesimal, the source is going to be constant during that time interval. We can then define the idea of energy flowing through an area over time. We can write that the infinitesimal amount of energy that crosses this area over an infinitesimal amount of time is proportional to the area and to the time interval. And we call this proportionality factor the flux. Give it the symbol F. So we can then write that dE is equal to F times dA times dt. Notice that in the right-hand side, you have two infinitesimals, and in the left-hand side, you only have one. Rigorously, we should have the square E instead of dE, but in practice, we're going to drop exponents on infinitesimals. Now, this equation is in fact still missing a physical ingredient, and that the energy depends on. Say, if your detector can be sensitive only in X-rays, but if the radiation shine unit is in, say, microwaves, then you're going to detect no energy. We conclude then that you have to define the frequency range in which you are measuring the radiation. So we can define now the specific flux, which is the net energy flowing through per unit area per unit time in a given frequency range. We call the specific flux F nu. So if we define all these intervals to be infinitesimal, so that the energy is constant in space, time, and frequency range, then we can isolate the flux. So the subscript nu in F nu and D nu denotes that these quantities are monochromatic. That is, they're measured in a single frequency. Now, in practice, we cannot measure monochromatic flux. We always measure a finite range of frequencies that we call a waveband. So when we measure a flux in a given waveband, says that our measurement goes from nu 1 to nu 2, what you are measuring is actually the flux as the integral of the monochromatic flux, of the specific flux, in frequency from nu 1 to nu. So the left-hand side of this equation is what is actually measured. The integrand in the right-hand side is a mathematical abstraction. The quantity F nu is an underlying function, an idealized monochromatic flux. Say that you have your spectrum like this. The monochromatic flux would be what you measured if your spectral band was infinitesimally narrow. You would measure one particular wavelength. In practice, you always observe with a bandwidth, with a finite size bandwidth. Now, so that the units of the specific flux come out correctly, the specific flux must be defined per hertz. Now, the unit of the flux is energy per area per time. The unit of the specific flux is energy per time per area per hertz. Finally, we can also define the bolometric flux, which is just the total flux integrated in all frequencies.